In this video, we are going to go ahead and continue homework 1 and go on to part B. So before that, I'm going to quickly summarize what we did in the previous video. Essentially, we had this problem here, 3 gravity-drained tanks in series, and our goal was to adjust the input flow rate into this first tank in order to reach a specific height set point in the third tank. And we derived from Bernoulli's equation, we got the material balance, and we were able to come up with a governing equation to kind of describe how the height changes with time, the liquid height level in the tanks. And then we went ahead and coded this up. So we ran this and we couldn't quite reach the set point in our third tank. We wanted to reach about 6.12 meters in height, and we could only reach 5.98. And this was due to the steady state offset that you encounter when you only have a proportional controller. So in this video, we're going to derive the equation for adding an integral controller component, and then we will also add to the code and show how this can improve reaching our set point. So something I initially neglected to mention is that we are deriving the dynamical equations for 2 gravity tanks connected in series rather than 3 tanks connected in series. It won't change most of our equations that we calculated, but that's just something to keep in mind. And so I'm going to get into that right now. Okay, so I went ahead and I basically wrote down all of our knowns, and I also made this little diagram right here, which is very similar to homework 1 part A, except we just have 2 tanks now. And what we want to do is we want to derive the dynamical equations to represent this problem. And we are putting in a proportional and integral controller into this example rather than only a proportional. So from part A, we had this dH dt term right here. The change in height of the liquid level over time equals 1 over the area times the flow rate in minus the area of the hole times the square root of 2gh. So I'm just going to go ahead and rewrite that here so we have it. And if we want to, we can write this in terms of the first tank and the second tank. So we would have A1 Qn minus AH1 2GH1. We also know that this right here is Q1. Remember that the volumetric flow rate is also equal to the velocity times the area, and that's how we get meters cubed per second. Oops. And we said with this 2gh term, the flow rate, Q out, is equal to this area of the hole times the square root of 2gh. So that's where that comes from. We also have dH2 over dt equals 1 over A2 Q1 minus Q2. Q1 is this value. We also know Q2 should be AH2 square root 2GH2. From part A, we know that the proportional only controller, we had Q in was equal to the initial flow rate in plus the KC value, which was the controller value specifically for the proportional controller, multiplied by the set point minus the last tank. In the part A, we had 3 tanks. Here we only have 2, so this would be the set point minus the second height. And this is also the error. So we multiplied our proportional controller term by the error, added it to the initial flow rate in, and that is how our controller was adjusting the flow rate in to reach the set point. This time, we are including the integral component. So I'm just going to call this the PI controller. Similarly, we still have Q in equals Q naught plus KC times the error. However, we now also have, unsurprisingly, an integral component. So we're going to call this Ki. It's just another constant that we can use to alter essentially what the integral controller does to our flow rate in, times the integral from 0 to time t of the error. And then this is data tau. In our case, tau is essentially the x-axis. Now, this question itself mentions the Fundamental Theorem of Calculus, which can be kind of written in a couple of different ways, but what we're focusing on here is if we have an integral from a to b of a function f of x, that is equal to f of b minus f of a, right there. So we can say, therefore, the derivative of an integral from a to some number, such as 0 to t right there, the derivative of a to some number we're calling x of f of x dx simply equals the function itself. The main thing we have here to keep an eye out for is this value has to match that value right there. But this value doesn't necessarily need to match. So that is why we can do it. We are going to call this integral the integral of the error. So when we take the derivative of this integral of the error with respect to change in time, which matches our upper bounds on the integral right there, we can say that this, the error, as our answer. Essentially, our reason behind writing it down in this way is so that when we code this integral component, we essentially are saying, instead of looking at everything from 0 seconds to the current time, just look at the current error, and we will be adding up those errors, and that is how this value will update. So the integral looks at the accumulated error. The proportional only looked at the current error. So we will essentially be adding up all of these error terms. So the error from 0 to 1 second, the error from the error from 1 to 2 seconds is some value, and that will all be added and multiplied by this ki. So we will go ahead and get into the coding section. So we are actually going to start out here by copying and pasting part A's code and just editing it a little bit, because they will be pretty similar. Our goal here is essentially to use Python to solve the set of dynamical equations in this part for 2 identical tanks with cross-sectional area of 1 meter squared, drainage hole of 0.1 meters squared. These are the same values as the tanks in part A. And we want to figure out where the set point for the second tank is increased from the initial steady state level when the flow through the tanks was 1 meter cubed per second. I'm going to change this back to 1,000 seconds. I'm going to lower the KC value just because I'm not quite sure kind of what we're going to be wanting. And I need to add our KI. Again, probably a small value. Just a few edits since we did copy this from part A. We can get rid of H3 and Q3 because we only have 2 tanks. Again, we can get rid of this right here for a third tank. Our error is the set point minus the height of the second tank. So this right here is where we need to edit our code. I almost forgot another thing that we need to add to this vector is our error integral. And I'll explain why coming up soon. These flow rates are good. This error equation is good. And as I was getting started saying, we need to adjust this right here. It's going to be like we just wrote down plus ki times our error integral. Our error integral is going to be calculated by returning this e value, because like we said, dE integral, so our dE int over dt was actually just equal to the error itself. And here, instead of having a vector with just 3 h naughts, we are actually going to write out h naught, and 0. So what this means is that the height 1, so the height of tank 1, starts at h naught. right here, the initial steady state height. Same with the second tank. And then this third number right here, we are basically saying that right at the start there isn't really any error, but this will change as time goes on, and that will then adjust the inlet flow rate right here. This method should be okay, and this is good, and we are going to say hplot equals results dot solve tplot. We would like an h1 plot, an h2 plot, and also we can have an error integral plot. Just call this h plot. We want to create a scatter plot for h1, h2, which this is all still good from our part A code. And we do not need this right here. We could plot this E integral plot, but as of right now, I don't think it is like extremely necessary. So let's see what happens when I run this. There is a good chance I missed something, but we will find out. Okay. So it looks like we have a little issue here. And we are completely diverging. So what I'm going to start off with is hope that maybe my KI was too high. And it looks like that was the problem. So you have to be careful with this integral controller gain constant, mainly because this term accumulates as the simulation goes on. So if both of these are big, we're going to have a huge increase in this flow rate in, and it's going to diverge. Right here we can see, as in the previous example, they both start at the same level, about 5.1 meters. Increase, decrease, and as you can see here, the height of the second tank is actually reaching our set point this time. In part A, we weren't reaching our set point due to that little steady state offset right there. And now that we have this integral component, we are able to dial this in exactly how we want it to be. So let's say I want this to be 2 times h naught. And I run this. We have 10.2, which is 5.1 times 2. So it looks like it's working out pretty good. Now you can play around with these values a little bit and see kind of what happens. Similarly, as in part A, when you increase this controller, the proportional controller gain constant, you get a few more oscillations. So let's see what happens when I put this pretty small and I increased that a little bit. Okay, so not quite what we're looking for. I think that's a little low. So let's stay around 0.01. Yeah. So it looks like with a proportional controller gain constant of 0.2 paired with an integral controller gain constant of 0.01, we're pretty steady pretty quickly. Doesn't take too long and stays really steady. And we don't go too crazy when we're adjusting the flow rate, which is also very important. This gets us there pretty fast with minimal kind of issues there. All right, so as promised, that was part B of homework 1. We have one more part to this homework 1 mini series in which we will derive the time-dependent material and energy balance equations of a continuous stirred tank reactor. And we will also do some coding there, and I will get into that in part C. So thanks for watching.